Hello again. So before watching this video that is more like solving problem for the sections 5 and 6 in chapter 29, please watch the video that I uploaded from the PowerPoint presentation that I had for my other class, because that gives you more like the definitions and warm you up for the calculation. So if you watch that video, you should already know what happens to mass when the object is moving very fast, meaning close to the speed of light, and what happens to its energy. So if not, please take like 30 minutes or so and watch that video first. According to Newtonian physics, we know that momentum is defined to be mass times the velocity. Now, we want to know what is a relativistic momentum. Okay, so what happens is that again, we need to kind of like work with this factor here, which was called the Einstein factor, right? So this is the Einstein factor, which is shortly 1 minus beta squared, and this whole 1 over square root of 1 minus v squared divided by c squared is called gamma or Lorentz factor. So this one is Lorentz factor. Okay, so if you want to find the relativistic momentum, it is enough to multiply the Lorentz factor by the non-relativistic momentum. The unit for the relativistic momentum is still same as the non-relativistic one, which is kilograms times meter per second. Let us take a look at exercise 2910, which says A, find the classical, and B, the relativistic momentum of a 3.90 kilogram mass. So M is 3.98 kilogram, moving with the speed of 0.965 c. So the speed is 0.965 c. So part A, find the classical momentum, and part B, find the relativistic momentum. Okay, so in the Newtonian physics, we know that P equals to mv, and I just need to go ahead and just substitute for the numbers that I have. So mass is 3.98 kilogram, and then V has the value of 0.965 times c, and c is roughly 3 times to the 10 to the power of 8 meters per second. All right, let's calculate this, and the answer is 1.15 times 10 to the power of 9. This is 9 kilograms meter per second. All right, for the relativistic momentum, however, I can just write that P equals to mv divided by square root of 1 minus v squared divided by c squared equals to. So I have already calculated mv in the first part, so I just substitute the value for it here, divided by square root of 1 minus 0.965 c whole squared divided by c squared. So in these two guys can cancel here, but just remember that 0.965 should be still squared. So this will gives me the value of 4.39 times 10 to the power of 9 kilograms meter per second. So you see that it is with this it is like a little bigger than the Newtonian momentum, and this is expected, right? Because as I told you in the previous video, the mass becomes bigger when an object is moving very fast. So here the object is moving very fast, so the mass becomes bigger, and when the mass becomes bigger, of course the momentum will increase. All right, so just suppose here that an object has the mass m naught. So instead of m, it has m naught, all right? So if this is the initial mass or the rest mass, then momentum can still be defined by m naught v divided by the Einstein factor. Now, in this equals to mv, we know that. So from here, I can say that m, which is the mass of the object who is moving, equals to m naught divided by square root of 1 minus v squared divided by s squared. Okay, so this m naught is the rest mass, and then m is the relativistic mass or the moving mass. Now, when v approaches to c, of course, this 2 becomes equal and 1 minus 1 becomes 0. The denominator is 0. So I can say that m approaches to infinity. So when this happens, according to the equation A equals to force divided by m, we can say that a constant force that is acting on an object generates less and less acceleration. Okay, so this gives one further way of seeing that the speed of light cannot be exceeded, right? Because then the acceleration becomes less and less, so we can never reach that speed, the speed of light. Also, as I told you earlier, we can find the rest energy according to this equation, right? And then E equals to mc squared for the objects that are moving fast. Okay, so this one is the rest energy. For example, on exercise 2912, it tells us to find the rest energy of a 0.19 kilogram apple. So mass is 0.19 kilogram. Okay, so we didn't know that the apple has a rest mass, but of course it has. Everything except from the photons have the rest mass. Okay, so this is just very simple. We just need to replace here in E naught equals to m naught c square. I need to replace the m naught by 0.19 kilograms, and then times 3 times 10 to the power of 8 meters per second squared. And then I can get E. Okay, made a mistake here. Second squared. I told you squared and then I just wrote it on top of the s. Okay, so here the rest energy will be counted to be 1.7 times 10 to the power of 16 joules. And still the unit is joules. The units do not change.